Hi, good morning, everyone. Today, let us try to learn about the transient response of a series RC circuit with DC excitation. So, excitation means giving an DC input using Laplace transform. So, Laplace means it will be in the form of S domain. So, this Laplace is also called as S domain, or this is also called frequency domain. So why frequency means S is equal to j omega, that is equal to j into 2 pi f. So here what is there? Frequency is there. That's why this is called frequency domain, or this is also called S domain way of solving. So previously you have been seen some videos in the same in my content which replicates about transient response of series circuit with DC excitation using time domain analysis. It's nothing but writing di by dt I equals c dv by dt. But there are some complications and it's very tough to solve. So we are going to simplify it by converting that all time domain functions into S domain. Let's try to find the transient response. So it's very simple to understand. Transient means this is available only for shorter time. For example, to take an waveform of so we are going to get a resultant waveform like this I of t versus t. You can see the curve will start from this point, it will go to the peak value and it will get settled down here. Okay, so this is the time we are going to call it as a transient state, and this time is called as a steady state. So you can see here this transient state or transient state is only for small duration. For example, if you mark this duration, this is 4 times the time constant. If you times the time constant as 1 second, and you can assume that this transient response are available only for an shorter time or shorter interval. So those responses are called as a transient response. So response means output, excitation means so input. So we are going for an DC excitation as an input for an RL circuit. We are going to find out the transient response or the transient output. Let's try to draw the circuit diagram for this. Okay, so how to draw the circuit diagram? Let's try to realize. So here you are going to have a DC excitation. This DC excitation is given to an R as well as an inductor. So this DC excitation I'm going to call it as V volts, and this is resistor R ohms. This is inductor in henries. So this is all in terms of time. So this is in terms of time domain. So now we are converting this time domain into frequency domain. When you convert this time domain into frequency domain, the network will be converted like this. So this is nothing but a resistor, and this is nothing but an inductor. So the input applied is a constant voltage. The Laplace transform of a constant is V by S. It's nothing but 1 by S. So I'm writing V by S. So the resistor is not an energy storage device. That's why the resistance is directly expressed in ohms. But here this is in Henry. After the transformation, nothing but multiplication with S into L. So this will be converted into ohms. So multiply the inductor with j omega. So this we can be expanded as a S is equal to j omega L. So the units of j omega L are once again ohms. So multiply the inductance value with 2 pi f, then we are going to get in frequency domain. Now this network is in which transformation? Frequency transformation. This way of solving is called Laplace transformation, and this is the input we are applying, which is called DC excitation, and we need to find out the current, which is nothing but I of S. Okay, so this is how we need to find out I of S, and we need to apply inverse Laplace for this, then you are going to get I of t. So this is our resultant solution. Let us see what kind of solution we have to derive is. So we need to get the current after solving this as I of t equal to v by r minus v by r into e to the power minus r by l into t. So this r by l is also called time constant. Tau is equal to L by R. Okay, so this is you can simplify it further also. This is V by R minus V by R e to the power minus T by tau. So this is what the response, or this is what the output current we need to derive by using this transformation. So just remember. So we will discuss it in detail in the further. Okay, now let us see here. So we have been got this. So now let's try to derive our expression. Current is entering, the terminals are positive, negative. Once again the current is flowing in series network. This is positive and this is negative. So try to apply Kirchhoff's voltage law in the loop. So you see here, whenever the what is the input voltage you are applying, which is nothing but plus V by S, and current is entering at positive, current is leaving. So whenever current is leaving, the leaving polarity of the voltage drop minus I into R. What is the I value? Nothing but I of S, the input current I of S into R value. What is the resistance offered by this branch? Which is nothing but R ohms, and current is entering at positive and current is leaving. Whenever the current is leaving, what is the polarity of this voltage source? Minus I of S into what is the resistance offered by this inductor, which is nothing but SL ohms, that is equal to 0. So now we need to find this expression. So V by S equal to, so pull out this all these negative terms to right hand side, then you are going to get I of S. So within this system you are going to get R plus SL ohms, but I require the expression of I of S. Okay, so how to find out the I of S? So the expression of I of S we will be getting as V by S divided by R plus SL ohms. So here I want to make this coefficient as 1. So how to make the coefficient as 1 is take L as an common. So then you are going to get V by S divided by, so I am going to take L as common, then you are going to get R by L, and L you are going to take common as S. So this is also in S, this is also in S. So this is V by S. When it comes to the numerator, it's nothing but this is L by 1. Let's go to the numerator. This is V into 1 by L divided by, this is 1 by S. This is nothing but we can write down it as S into S plus R by L. Now we need to solve this expression. So now this expression can be written as so we are going to get V by L. So you can expand this as by partial fraction A by S plus, so we are going to get A by S plus B divided by S plus R by L. So from here you can take the LCM is S into S plus R by L, and here you are going to get A into S plus R by L plus B into S. So from here we are going to cancel out the denominator, and let us try to substitute S is equal to 0. When S term become 0, you can see here the B term doesn't exist. Therefore, you are going to get V by L is equal to A into S is 0, which is nothing but R by L. L will get cancel out, and you are going to get V by R is equal to a value. So the unknown constant A we have been find out. And next one, coming to the next one, substitute S plus R by L equal to 0, then automatically you are going to get S is equal to minus R by L. So substitute in this equation, then you are going to get V by L. So this S is equal to minus R by L, A term will get cancelled, that is equal to V into S term is minus R by L. L will get cancelled out, and we are going to get minus V by R is equal to B. So these are the values of A and B which are known to us. Now let us try to substitute all this in our equation. So the ultimate equation of I of S is equal to, so the ultimate equation of I of S is equal to, what is A value? It's nothing but V by R divided by S plus, what is the B value? So here you are going to get a minus V by R divided by S plus R by L. So this is what the exact equation we require. So now this is in S domain, but already I told I want this to be transformed into time domain. I'm going to apply inverse Laplace transform. So this will be inverse Laplace transform of I of S is equal to I of t, and inverse Laplace, and we already know that inverse Laplace transform of 1 by S is equal to 1, and inverse Laplace transform of 1 by S plus A. So here it is plus A, you are going to get e to the power minus A. Whatever the polarity you have here, the opposite polarity will be replicated here. So the inverse Laplace of 1 by S is nothing but 1, therefore 1 is nothing but V by R minus, and here you are going to get V by R into e to the power minus, what is the value of A here? A is R by L into T. So here you have been got the two parts. Okay, so this is what the ultimate equation we require. Okay, so this first part is called as steady state, and this part is called as transient state. Okay, so this is called steady state and this is called the transient state. So when you find this equation, I'm going to plot this current expression. So this is nothing but t, and this is nothing but the expression of I of t. Okay, so how we are going to get it is, so when we draw this expression, so this is nothing but t, is nothing but I of t. You can see this curve. So this curve is an exponentially rising curve. Okay, so only this curve. So we are going to get an exponential rise like this, and this value is V by R into e to the power minus R by L into t. So V by I is nothing but the current. The current is exponentially rising, and this time we are going to, the exponential which is rising is called as transient state. After that it achieves a state which is nothing but V by R, and it maintains a constant magnitude which is nothing but V by R, and this state I'm going to call it as steady. Steady means the value is fixed. So the inductor has been, what happening to the inductor is the inductor has been charging. So it has been charged and came to an steady and it has been fully charged. Now the inductor is the state of a fully charged. Now condition of the inductor is this is fully charged. This how this expression helps out to find out. So coming to this transient state, so this transient state already I told this, when you give this voltage, this transient will occur and this transients will settle out so 4 times. So this is nothing but 1 tau, 2 tau, 3 tau, and these are settling at 4 times the time constant. After the 5 tau, automatically this is settled, the magnitude is constant. That's why this is called steady state. The output is steady, or this is called the steady state. So here we are going to get 4 tau. So this 4 tau I already told for how much time the transient is present is present very for lesser time, 4 into 1 second, then automatically you are going to get as 4 seconds. You just understand. So whenever you turn on an RL network or a fan or induction motor, the transients are present only for 4 seconds. So you can see here you have been turned on the fan, and the fan will try to reach the required speed. So 100 rpm, 200 rpm, and it reaches 500 rpm. And after 4 seconds it will try to run constantly, where this is called 1500 rpm. This 1500 rpm is called as a steady state. So it is trying to suddenly it will give a jerk, and slowly it will try to pick up. The slow pickup method is called transient state. Now the inductor is fully charged, and we need to find out the voltage across the resistor. So voltage across the resistor is nothing but given by I of t into R. So already we have the I of t value as, so you can see here the I of t value already we are having from here, as I am taking this V by R as an common term. I am going to get 1 minus e to the power minus R by L into T multiplied with R will get cancelled. The voltage across the resistor is given by V into 1 minus e to the power minus R by L, which is once again an exponentially reciprocal, like this, the same characteristics it is going to exhibit. Now, similarly, try to find out the voltage across the inductor. The voltage across the inductor is given by the formula V equal to L d I by dt. So, let's write down the L, and we are going to differentiate the I of t. What is I of t we have been got? So, we have been got it as V by R minus V by R e to the power minus R by L into t. So when you differentiate it, differentiation of constant is how much? 0. Differentiation of this term is V by R, and differentiation of e to the power x is e to the power x into the differentiation of internal term is nothing but minus R by L into 1. So when you go further, you see here L into, so plus into plus, I mean minus into minus is plus, which is nothing but V by R e to the power minus R by L into T is nothing but R by L. So L will get cancelled out, and R will get cancelled out, and we are going to get V into e to the power minus R by L into T. You can see here this is an exponentially decaying curve. So it's nothing but e to the power minus t by tau. So here we have to remember one concept. Time constant is nothing but is defined as ratio of inductor divided by resistor. So this is nothing but L by R. So you can see this equation of I of t. So here I of t you can also write down it as V by R minus V by R into e to the power minus R by L into t. So this we can expand and write down it as V by R minus V by R. So e to the power minus t into tau. So this if you bring to the denominator is nothing but L by R, which is nothing but t by tau. So this is the perfect. This I of t is called the transient response or transient output of an which network? R L network with a DC excitation in which domain? S domain. So want we'll have some small brush up. So we have been converted this time domain into Laplace transform for simplification, and we expressed this in R ohms, SL ohms. We applied a small KVL, and we have been find the expression of I of S. So from I of S, we have been got V by S, and this is in S domain. We want to solve it. We applied partial fractions method, and we find the values of A value as well as the B value. After finding the A and B value, we substituted in this equation, and we applied inverse Laplace transform and we got this expression. So we had already told this is the time taken by the waveform to, and this is the time taken by the a fan to start, and after starting it is into 1500 it's called steady state. This is the time when you turn on the fan, it will take some time to come to a steady state. The time is called transient state and the waveform is fulfilled. So therefore the expression of I of t is v by r into, so we will try to find out what is the voltage across this inductor. So the voltage across this inductor we are going to call it as vr. The voltage across the capacitor we are going to call it as vl. So the expressions for this are here. So this is the voltage across the resistor and this is the voltage across the inductor. Hope this video is very useful. Please like to our channel, share with your friends and subscribe to kvthulasi electric vehicle channel. So feel we will promote this channel such a way that it will reach to all the needy students to prepare well for their academic. Thanking you, yours Ram.